Termination for convenience clauses and property seizure clauses can appear in subcontractor agreements. Such clauses are generally legal under United States law. Termination for convenience allows the owner to terminate the contract at any time, even if the subcontractor isn't in breach. This provides flexibility for the owner to adjust to changing circumstances. The clause on limited recovery for subcontractors protects the owner from potentially significant damages in the event of termination. Seizure of property authorizes the contractor to take control of the subcontractor's property if the subcontractor breaches the contract. Subcontractors who are in a weaker negotiating position or who need the work may agree to such terms. This may occur in situations where the owner has a strong market position, the subcontractor is a small business with limited resources, or the subcontractor is desperate for work. These clauses pose significant risks to subcontractors, including financial loss. Subcontractors may only receive limited compensation for work performed, potentially resulting in lost profits. Subcontractors have little recourse if the owner terminates the contract without cause. Being terminated for convenience can damage the subcontractor's reputation and make it difficult to obtain future work. Subcontractors should consider the following precautions before signing such contracts. Firstly, negotiate terms. Attempt to negotiate more favorable terms, such as higher compensation or the right to recover lost profits. Secondly, seek legal advice. Consult an attorney to review the contract and ensure their rights are protected. Thirdly, evaluate risk. Carefully consider the risks associated with the contract and determine if they are acceptable. Explore other opportunities or contracts that offer more reasonable terms. Several key aspects of electrical work and related codes, specifically focusing on grounding, bonding, and conductor sizing, are discussed. The first main topic is grounding electrode conductors. These conductors connect the grounding electrode system to the electrical system's grounded conductor, typically at the service equipment or separately derived system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, or, for separately derived systems, the size of the derived and grounded conductors. The relevant table for sizing grounding electrode conductors is found in the National Electrical Code, specifically Table 250.66. This table provides the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. For example, if you have copper service entrance conductors of a certain size, the table will specify the minimum size of the copper grounding electrode conductor required. Similarly, if you are using aluminum or copper-clad aluminum conductors, the table provides the appropriate size for those materials. It's crucial to use the correct table and follow the NEC guidelines to ensure proper grounding and safety. The second key topic is bonding jumpers. Bonding jumpers are used to connect metallic parts together to create a low impedance path for fault current. This is essential for clearing faults quickly and safely. There are several types of bonding jumpers, including main bonding jumpers, equipment bonding jumpers, and supply-side bonding jumpers. The main bonding jumper connects the grounded conductor, usually the neutral, to the equipment grounding conductor at the service equipment. Its size is determined by the size of the service entrance conductors, similar to the grounding electrode conductor. Again, Table 250.66 is often used to determine the minimum size of the main bonding jumper. Equipment bonding jumpers connect metallic enclosures, such as electrical boxes, cabinets, and raceways, to the equipment grounding conductor. This ensures that all metallic parts are at the same potential, minimizing the risk of electric shock. The size of equipment bonding jumpers is determined by Table 250.122 based on the rating of the overcurrent protective device, such as the circuit breaker or fuse, protecting the circuit. Supply-side bonding jumpers are used in separately derived systems, such as generators or transformers, to connect the grounded conductor to the equipment grounding conductor on the supply side of the system. The size and requirements for supply-side bonding jumpers are similar to those for main bonding jumpers and are also based on the size of the derived and grounded conductors. The third important aspect is conductor sizing and ampacity. The ampacity of a conductor refers to its current carrying capacity, which is the maximum amount of current in amps that a conductor can carry continuously under specific conditions without exceeding its temperature rating. The ampacity of a conductor is determined by several factors, including its size, insulation type, and the ambient temperature in which it is installed. Table 310.16 in the NEC is commonly used to determine the ampacity of conductors based on their size and insulation type. For example, a 12 American wire gauge copper conductor with THHN insulation has a certain ampacity, typically around 20 or 25 amps, depending on the specific conditions. However, it's important to note that this ampacity may need to be adjusted based on other factors, such as the number of current-carrying conductors in a raceway or cable, and the ambient temperature. If there are more than 3 current-carrying conductors in a raceway or cable, the ampacity of the conductors must be derated according to Table 310.15 cone. This derating factor reduces the allowable ampacity to prevent overheating. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity must be derated to 80% of its value in Table 310.16. Similarly, if the ambient temperature is higher than 30 degrees Celsius or 86 degrees Fahrenheit, the ampacity must be corrected using the correction factors provided in Table 310.15 bone. These correction factors reduce the ampacity to account for the higher ambient temperature. When sizing conductors, it's essential to ensure that the conductor ampacity is sufficient to carry the load current. The general rule is that the conductor ampacity must be at least 125% of the continuous load. A continuous load is defined as a load that operates for 3 hours or more at a time. For example, if you have a continuous load of 20 amps, the conductor ampacity must be at least 25 amps. This ensures that the conductor is not overloaded and can safely carry the current. In addition to ampacity, it's also important to consider voltage drop when sizing conductors. Voltage drop refers to the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor length, the load current, and the conductor resistance. There are various voltage drop calculators available online that can help you with this calculation. If the calculated voltage drop exceeds the recommended limits, you may need to increase the conductor size to reduce the resistance and minimize voltage drop. Furthermore, equipment grounding conductors play a crucial role in electrical safety. These conductors provide a low impedance path for fault current to return to the source, allowing the overcurrent protective device to quickly trip and clear the fault. The size of equipment grounding conductors is determined by Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. For example, if you have a 20 amp circuit breaker, the minimum size of the copper equipment grounding conductor is typically 12 American wire gauge. It's important to use the correct size equipment grounding conductor to ensure that it can safely carry the fault current. In addition to sizing, the installation of equipment grounding conductors is also important. They must be securely connected to all metallic enclosures, such as electrical boxes, cabinets, and raceways. This ensures that all metallic parts are at the same potential, minimizing the risk of electric shock. When running equipment grounding conductors in raceways, they must be installed in the same raceway as the circuit conductors. This ensures that the impedance of the grounding path is minimized. It's also important to avoid creating ground loops, which can occur when there are multiple grounding paths. Ground loops can cause unwanted current flow in the grounding system, which can interfere with sensitive electronic equipment. Surge protection is another critical aspect of electrical system design. Surge protective devices, or SPDs, are used to protect sensitive electronic equipment from voltage surges caused by lightning, utility switching, or other transient events. SPD are typically installed at the service entrance, as well as at downstream locations to provide layer protection. There are 3 main types of SPD: Type 1, Type 2, and Type 3. Type 1 SPD are installed at the service entrance and are designed to protect the entire electrical system from large surges. Type 2 SPD are installed at distribution panels or subpanels and provide protection for branch circuits. Type 3 SPD are installed at the point of use, such as at an outlet, and provide protection for individual pieces of equipment. When selecting an SPD, it's important to consider its surge current rating, which is the maximum amount of surge current that the SPD can safely handle. The higher the surge current rating, the better the protection. It's also important to consider the voltage protection rating, or volts peak, which is the maximum voltage that the SPD will allow to pass through to the protected equipment. The lower the volts peak rating, the better the protection. SPD should be installed in accordance with the manufacturer's instructions and the NEC. They must be properly grounded to ensure that they can effectively divert surge current to ground. Regular inspection and testing of SPD are also important to ensure that they are functioning properly. Furthermore, understanding the requirements for electrical panels and overcurrent protection is essential for electrical safety. Electrical panels, also known as load centers or panel boards, are used to distribute electrical power to various branch circuits in a building. They contain overcurrent protective devices such as circuit breakers or fuses, which are designed to protect the circuits from overloads and short circuits. The size of the electrical panel is determined by the total load that it will serve. The panel must have sufficient capacity to accommodate all of the branch circuits, as well as any spare capacity for future expansion. The NEC requires that electrical panels be readily accessible and not obstructed by anything that would prevent access. They must also be properly labeled to indicate the circuits that they serve. Circuit breakers and fuses are designed to trip or blow when the current exceeds their rated value. This protects the wiring and equipment from overheating and damage. It's important to select the correct size circuit breaker or fuse for each circuit. The general rule is that the circuit breaker or fuse should be sized to protect the smallest wire in the circuit. For example, if you have a 14 American wire gauge wire in the circuit breaker or fuse should not exceed 15 amps. It's also important to use the correct type of circuit breaker or fuse for the application. There are different types of circuit breakers and fuses designed for different types of loads, such as lighting, motor, and appliance circuits. Ground fault circuit interrupters, or GFCIs, are another important safety device used in electrical systems. GFCIs are designed to protect people from electric shock by detecting small imbalances in the current flowing through a circuit. If a ground fault is detected, the GFCI will quickly trip and interrupt the circuit, preventing electric shock. GFCIs are required in wet locations such as bathrooms, kitchens, and outdoor areas where there is a higher risk of electric shock. They are also required in construction sites and other locations where portable tools and equipment are used. GFCIs can be installed in the form of circuit breakers or receptacles. GFCI circuit breakers provide protection for the entire circuit, while GFCI receptacles provide protection only at the point of use. Arc fault circuit interrupters, or SIs, are another type of safety device used in electrical systems. SIs are designed to protect against fires caused by arcing faults. Arcing faults can occur when there is a loose connection, damaged insulation, or other condition that causes electricity to arc between conductors. SIs are required in many locations, such as bedrooms, living rooms, and dining rooms, to protect against the risk of fire. SIs can be installed in the form of circuit breakers. SI circuit breakers provide protection for the entire circuit. When working with electrical systems, it's important to follow all safety precautions and use appropriate personal protective equipment, or PPE. PPE includes items such as rubber gloves, safety glasses, and insulated tools. Before working on any electrical equipment, it's important to energize the circuit and verify that it is energized using a voltage tester. Lockout-tagout procedures should be followed to prevent accidental re-energization of the circuit. It's also important to be aware of the potential hazards associated with the electrical work, such as electric shock, arc flash, and electrocution. Proper training and experience are essential for working safely with electrical systems. Regular inspection and maintenance of electrical systems are also important to ensure the safe and reliable operation. This includes checking for loose connections, damaged wiring, and other potential problems. Any problems should be corrected promptly to prevent electrical hazards. By following these guidelines and safety precautions, you can help ensure the safe and reliable operation of electrical systems. The NEC provides detailed requirements for the installation and maintenance of electrical systems. It's important to be familiar with the NEC and to follow its requirements when working with electrical systems. Continuous learning and professional development are also important for staying up to date with the latest electrical codes and technologies. This includes attending training courses, reading industry publications, and participating in professional organizations. By investing in your knowledge and skills, you can become a more competent and confident electrician. Ensuring electrical safety requires diligence, knowledge, and adherence to established codes and practices.